So let us continue with the explicit calculation of what Boole calls condition of possible experience. And of course, in Boole's times, there were only classical conditions of possible experience. So we will give now classical bounds on probabilities and expectations and joint probabilities, joint expectations, and so on and so forth. And the connection to Boole was actually discovered by Pitofsky. So let's just start by mentioning what one should do. One should geometrically reinterpret. This is the basis of the method. Geometrically reinterpret or present the probability distributions as convex polytopes. And the first researcher who did that was Froissart. Also Garg and Mermin did that, and Pitofsky, and Cyrilson and others later on. What you do is you form a bouquet of n what you consider relevant combinations of either single or joint dichotomic elementary outcomes or events, and then you arrange these bouquet into n tuples, and you consider them as kind of rows, and the vector form will come later then. Because you will consider them, you will consider the values of these rows as coordinates of vectors with respect to some orthonormal basis. This is at the basis of the basis of the method, and let's just suppose that there are k two-valued states on the pertinent context. But mind you, the number of two-valued states is independent of your choice, of the bouquet you choose. You always have k. And you apply these valuations to the chosen n combinations of dichotomic outcomes events, and form k row tuples, let's say, yeah, that will be interpreted later as components of vectors with respect to a Cartesian basis. So you interpret these n tuples as vectors in an n-dimensional Hilbert space. Yeah, by interpreting the 1 or 0 or -1 or whatever you have as coordinates with respect to some orthonormal basis, let's say Cartesian basis. And then you stack these k rows on top of each other. And the resulting matrix is the Travis matrix if you are dealing with probabilities, or kind of Travis matrix if you have more general expressions that can be rewritten in a linear fashion in terms of probabilities. So you consider then the convex polytope formed by interpreting these k n tuples as vertices of the polytope. Yeah, so you got the vectors first. The vectors come from the two-valued states, interpreted as components or vector coordinates with respect to a particular basis, and from these vertices you form a convex polytope. And according to the Farkas-Minkowski-Weil main representation theorem, this convex polytope has equivalent representations. On the one hand, it's a representation is in terms of its vertices, And on the other hand, this is in terms of its facets or intersecting half spaces. And these intersecting half spaces, they are the basis, they are basically inside, outside of this polytope kind of thing. These are the conditions of, these can be identified with Boole's conditions of possible experience. And the computation that yields these half spaces from the vertices, this is called the Hull computation. And we will be mainly concerned with Hull computations. Yeah, so we will need to find all two-valued states, find all the vectors, and then do the Hull computation, and then you have the Boole Bell type inequalities. This is basically the approach chosen by François and Garg, Mermin, and Pitowski and others. Just notice that if one is dealing with expectation values, then instead of the two-valued states, the affine transformed expectation values have to be inserted for the Travis matrix, or for the matrix entering these computations, the Hull computations. Now, let's talk about programs to compute optimal Boole Bell type inequalities. So these are basically programs that solve the Hull problem. And the main program I will be using here, there's an alternative package, LRS, by David Avis, that takes the same input and yields the same output, in the same form at least. The main package I will be using is Kome Fukuda's cntd package. It's an implementation of a particular method that is called double description method for either generating all vertices if the facets are known, or what we will be most interested in, the reverse operation, convex Hull computation, that is from a set of vertices derive the Hull, the convex Hull, that is the half spaces, the linear inequalities that characterize this linear convex polytope. Yeah, and we will be mainly quoting from a Python wrapper that has been implemented by Matthias Trofaies. There are basically two ways to access cntd. One is go directly to Fukuda's homepage, to the cntd homepage by Fukuda at the ETH, Eidgenössische Technische Hochschule. Please don't forget to install, if you choose that way, install GMP. This is a library for arbitrary precision arithmetic. But in what follows, we will be mainly using a Python wrapper for cntd-lib. And the first thing is you have to if it's not installed on your box, you have to install Python. You can do that by either going to python.org or by, let's say in Windows, from the Microsoft Store. This is free. You should check if Python after installation is installed correctly. You type in Python and it should respond with 3 arrows. And if that is the case, you have successfully installed Python and you can exit with this command. Check also if pip is installed. That's a utility to install additional packages. And you can either go to the page of Python cntd-lib to inform yourself of the package, this is optional, or immediately type in pipe install Python cntd. And if everything works out correctly, it should then read successfully installed a version of the Python cntd. Of course, I believe in your case, if you do that later, you will install later versions of this, and then you are ready basically to go. And I shall show you now how to do the high computations for particular first simple situations and configurations. The first thing is, once you are in Python, yeah, you first type in Python. You basically say import cdd, which imports the package into Python. Then you say cdd matrix 1 and t is the Travis matrix, and basically contains the values of the two valued states with a 1 added. Yeah, so basically you have a column consisting only of ones, and this is the Travis matrix. This gives you the vectors, the Travis matrix, yeah, of the polytope. And then you say, well, this is a polytope. You tell cdd that this is a polytope with this statement. And the actual height computation you perform by issuing polyget inequalities. Yeah, and then you end up with a set of a list, and this list basically consists of, in the form of b minus a, consists, and this can be reinterpreted as the Haller representation. You have the b here that is in the list. This is with the inequality, you have the b here, and you have a minus a here that corresponds to the a here, and so these inequalities here actually are the half spaces. Define you the half spaces, the Bell type inequalities, and you should just rewrite them accordingly. Yeah. And the x they represent the weights corresponding to the bouquet of observables you chose. You can print out the results then on your screen or on file. Use this by typing something like this, and then you are finished basically. So let's give some examples. The first example is a very elementary example. It consists just of an isolated context with two mutually exclusive binary observables. Yeah. So you have basically a single Boolean algebra. This is observable O1 and this is observable O2. Of course, if this is a Boolean algebra, O1 is the complementary of O2 and vice versa. And you have just two valued states, which are encoded by this Travis matrix. And if you do all the statements that I gave you, you can even copy them from the screen here, you will end up with such a response, which you have to translate into these algebraic statements that make sense. There is one thing that needs to be taken into account though. If there is a linearity involved, then this says here that one linearity has to be interpreted as equality instead of inequality, and this is an indication that this convex polytope is not full dimensional. That is, it doesn't fill the entire three-dimensional or two-dimensional space. Yeah, so this is you have always to watch out a little bit. If there is a linearity involved, and then you have to do equality instead of inequality. So let's then come to standard derivations of involving isolated non-intertwining contexts. And the first one is two binary observables that are not a part of a single context, but that are that constitute two contexts. Yeah, so you have the possibility that you have all the four possibilities. Yeah, both are false, and you consider the joint probability, or one of them is false and the other true, or both are true, and so on and so forth. So you basically get a Travis matrix. If you want this bouquet here, you get this kind of Travis matrix that is indicated here with these colors. And you enter the Hull computation, and you find out some inequalities, which I won't go deeper into. There's nothing exciting here. The same if you do this with not with binary observables with values 0 and 1, but binary observables with -1 and +1, often called expectation values. If you are, for instance, for speed states, and you have again just a Hull computation here. This is the output. Nothing exciting here. I will not go too much into details here. Same. If you have, yeah, it's basically the same as those. I mean, this is just a representation of what's going on here. Yeah. So this is a consistency check if that is okay. Yeah. Because we derived previously those probabilities and expectations, and this is just a check if this is okay. So let me go beyond that. Beyond that, you can have three isolated contexts with two mutually exclusive binary observables, -1 and +1, and you can consider with three binary observables, you can have three joint observables, E1, E2, E1, E3, and E2, E3. You have to multiply them. You get the table here, and the table gives you the Travis matrix. You enter again the Travis matrix into the definition of a polytope and into the Hull computation. And what you get is you get the super Zanotti inequalities. So this is a fast way of getting maximal inequalities called after their discoverer, Suppes and Zanotti. It's quite an easy way to solve the whole problem and obtaining these equations. And there is something interesting here, but I just want to mention these classical high computations. Don't want to discuss discrepancies with quantum predictions, but there is something interesting here already. And then you can have 4 isolated non-intertwining contexts. You have this bouquet here of joint expectations. Usually one has this idea that you have a source, a singlet source, let's say, and you measure the observables O3 and O4 on the left, and O1 and O2 on the right. And if you do that, you end up with the so-called Clauser-Horn-Shimony-Holt inequalities. And in order to do that, you have to give the Travis matrix, the corresponding Travis matrix. It's this one here. And the resulting output is this. Everywhere where you see a 2, this indicates that these are relevant for the corresponding permutated Clauser-Horn-Shimony-Holt computations. And the other ones are also true, of course, but they are not so exciting here. This says just that E24 is bigger than or equal to -1, which should be right if one is dealing with joint expectations of observables that of 2 observables that can either be -1 or 1. So it's quite easy to generalize this to more directions on either side. Witowski and myself have been doing this for 3 observables per side. It should be rather a 3 here. And yeah, you can find the Travis matrix easily, basically by, again, just computing it. Just don't forget to add this vector here. And you can, according to the output, the higher computation, you can find new types of inequalities which are not contained in the Clauser-Horn-Shimony-Holt inequalities, set of inequalities. They also contain Clauser-Horn-Shimony-Holt inequalities, of course. Probably I should note that one often assumes equivalent single outcomes for which the single expectation values turn 0. And these have been then generalized to general types of inequalities on N and M observables on on either side of this EPR explosion type scenario. Okay, now let's go to probably the last and most interesting type of computation, that is intertwining contexts. Intertwining contexts. Let's just consider the simplest case of a firefly kind of a configuration. We had this before. Remember, these were just 3 here and 3 here, and this is the intertwining atom here. Yeah, if you look at the Travis matrix, we have derived the Travis matrix for this configuration earlier. You have it here. You put it in the CDD package, and you obtain an output. And here you have again this linearity issue. So you don't have inequalities, but just equalities. Let's go to the pentagram house type scenario. I drew it as a house because of Professor Kalmbach, who studied this long time ago. The Travis matrix is from Wright, John Wright, the creator of the generalized Urn model. And with this, you can easily read off the probability distribution, yeah, for the atoms on this hypergraph. Yeah, so basically you get, where is it? 1, 2, 3. You get this here, yeah, and then you get this atom that is not an intertwining atom, and what remains is this here. Yeah, one can talk a lot about this again, but I'm particularly interested in this because this basically gives you a generalized Urn model, but I wouldn't go too deep into that. I will just mention that Boole and Stairs published an inequality that can be easily derived by just adding, let me just erase that here before I draw it anew, by just adding the probabilities of all intertwining atoms. Yeah, and if you do that, you end up with such a sum, which here's a 2 missing. Yeah, is less than 2 times all the weights, the sum of the weights, and this is of course equal to 2. So all of this here, the sum of the probabilities of the intertwining atoms, is smaller than or equal to 2. And this is also violated by some quantum prediction. So this was derived by Boole and Stairs in this publication. So, but this is no high computation. Yeah, we just gave the probabilities, and that was it. Yeah. If you do the high computation for affinely shifted observables, and do the high computation for a particular bookcase here, which I marked here by these yellow boxes. If you do that, you end up with a Travis matrix that is that looks like this. And of course, here is the input into the Hull computation. This is the vertex representation of this correlation polytope. And voila, you have an H representation. And this is the famous Glasgow et al. Type inequalities. Yeah. And let me just add here that, at least in my opinion, the art here is to figure out which bouquet is correct. But once you put in the bouquet, it's quite easy to derive those inequalities with this method. Okay, let's stop here for a while and leave it at that and come back with deriving some other computation, some other bounds that may be interesting from a classical versus quantum mechanical point of view. Thank you for your attention so far.